Okay, welcome back to our final section in Chapter 11. This one is kind of one that just takes all of the functions we've learned about this year, or most of them, and kind of gives us ways to find models for those functions. Basically, if we can take data points, plug them into a calculator, and figure out what an equation would be that would represent it or approximate the data the best. So our target for today is using a graphing calculator to find the model, or model, word for that is equation, for a given set of data. Okay, models for two variable data. These are four of the basic types of data we've looked at, or models we've looked at. Linear data, if you remember, that's straight line. We didn't really do much with that this year. That's more of an algebra one and geometry data. The model is y equals mx plus b. Quadratics, those are the U-shaped graphs. Remember, they can be right side up or upside down. Cubic models, those are the S-shaped curves of something like this, one way or the other. So they weren't both the graphs, but those are just ways that we might look. Exponential, we have ways they look like this. If we had growth models, decay models, look something like this. But those are the different shapes that we have. We're going to use our graphing calculator to see if we can approximate those shapes and hopefully come up with a model to represent our data. And I forgot to mention on the last slide, but if you need to rewind it, go back. You want to have those pictures in your notes because it's going to be the easiest way for when we graph these to kind of see what model we have. So to do regression analysis, that's what we're going to do today. Sounds pretty fancy, doesn't it? You go home or you get done with this and your parents ask you, what were you watching on the video? You say, I was watching regression analysis. And I learned how to do regression analysis for various data types. Now, what's for dinner, mother or father? Right? I don't say that. But it sounds really fancy. And really what you're doing is you're using a graphing calculator to find just the equations. So it's letting the calculator do the work for you. Here are the steps. If you haven't got them down yet, before I move on, pause it and get these values down. First one is enter the data. And that's where you press in blue, stat, enter 1. So kind of over here, blue is buttons you press. So we'll put that in blue to be consistent here. So to enter the data, you do stat, enter, or 1. You turn on stat plot. You hit second y equals, set window, press window, graph points, decide on the function type, press graph, and then do the regression, hit stat, calc, in either 4, 5, 6, or 0. Those are the choices we're going to use today. And sometimes you have to do more than one to kind of find the one that works the best. Okay? We are only going to do one problem. Okay? So make sure you get this down before you move on to the next slide. Like I said, we're only going to do one problem, and we're going to do lots in class tomorrow. And if you don't have a graphing calculator, it's kind of it's pointless to do too many of these because it's watching you push the buttons. So if you just have this steps down once and you kind of have this as a reference, so if you're in class, what to do, you can always look back on it then as well. So find the model of the best data. So what we're going to do is we're going to go to our calculator, and hopefully you wrote those values down. If you didn't, here, pause it on the screen. Okay, and then when you got them written down, come back. So if you got those values down, we are going to follow the directions they gave us. So we're going to hit stat, and we're going to go to edit, or 1, and we're going to clear the list. If you remember, you go up to list 1 and hit clear. There are going to be two lists here. Okay? X values, they're going to be your list 1. Y values, they're going to be list 2. That's just how we're going to do it to be consistent. So for list 1 is 1, 2, 3, 4, 5, 6, and 7. Okay, make sure you got them all in correctly, and then you're going to go over to list 2. If you haven't already cleared that list, do so. And we're going to put these values in: 24, 21, 17, 14, 9, 5, 2. Notice they line up across from each other. Perfecto. So we are going to graph these points to see if they work. We have to turn our stat plot on. If we hit second y equals, we hit plot 1, we hit enter, we're going to turn it on. So we arrow over to on. That's the other way you do it. Just hit y equals, and you'll look up here, the plots. If they're not highlighted, they're off. So we can see plot 1 is highlighted. If I just go up and hit enter on plot 1, I've just turned that plot off. I want it on though, so hit enter. The way I showed you is kind of the old-fashioned way. This is kind of the new way to do it. So if we want our plot on, just go to y equals and turn the plot on. We want to go to the window and adjust our window. Well, how do we know what our window is going to be? Well, the smallest x value is 1. So our x minimum has to be some value smaller than 1. I'm just going to put 0. I'm going to keep it close. I want to keep this window just the right size. My y value, the smallest one, is at the end. It's a 2. So I'm going to, x value, the biggest one, is 7. So I probably can keep 10 as my biggest value. My minimum, we just saw for y, well, that was 2. I'm going to put my y minimum to 0. My biggest y value is 24, so I'm going to make my max be 25. And now you should be able to see the entire thing. And you can see on mine, it already kind of cheats and shows you the graph. Here's the points. So to me, when I line these values up, I look like, to me, I could just take a line and kind of draw it right down the middle. So to me, this looks linear. So this is approximate. Now, is it going to be exact? No, because my line I just drew freehand doesn't get all the points. But my graph can actually, I can come up with an equation that should come pretty close. So we've decided we think it's linear. I decided I think it's linear. Nobody's here to argue, so I'm going to do a linear regression. So I go to stat and calc, like I just did right there, and we think it's a linear regression. Linear is 4. Remember the choices that we had that we're going to use, I should say, in the direction of the previous slide were, let me get back here, directions were, in my notes, remember, it's 4, 5, 6, or 0. We think it's a linear, quadratic, a cubic. We're not going to do quartics. Let's see what 0 is. We could do quartics. Linear and exponential regression, I should say. That's what REG stands for. So it's not exponential. We know it's not a cubic. It's not a quadratic. That's 5. It is a linear. Now there's 2 types of linear. We're going to go with the AX plus B instead of the A plus BX. It would technically work, number 8. You just don't want to, we normally have A as a coefficient of X. So our MX plus B form, we're going to stick with 4. So just use this one. Linear regression, we're going to hit enter again, and since we already have our values in L1 and L2, it automatically plugs them in for X and Y, and here is the equation it comes up with. Now if you just write down y equals ax plus b, a equals negative 3.789 or 79 or whatever, and 28.29 for b, that's not an equation. The answer or the model, the equation would be approximating those. So y equals negative 3.79x plus 28.29. That would be the equation that models the data. Now, I wouldn't just assume it hit, because what if you pick the wrong regression model? I've done that before. So in case you do something like that, you want to check and see if it lines up. So we're going to plug in our equation. So we wrote it down on the previous slide, right? Negative 3.79x. So let's put that down, negative 3. Now, because we're approximating, keep that in mind, that's going to throw off the answer a little bit, because we did round. But it should be pretty close. 20 plus 28.29. If we go to 2 decimal places, that should give you a pretty good estimation. So we graph it, and look at that. Our line comes out pretty close. Okay, pretty close to the one I actually drew. So I would say this is linear. We approximated it. The equation cuts through most of the data. It's not going to touch all of it, because real life data, it doesn't touch every single data piece, but it should come close. So now, what's the point of this? Now in the real world, when you collect data and you find a pattern that it fits one of those types of models, and you create your own model, you can predict things for the future. You can predict what prices will be in the future. You might predict population growth off of this. You can predict how much housing market might change if trends continue. So people, mathematicians in the real world, economic people in the economy that are making decisions, economists, the word I was looking for, they use these models and these types of regression techniques to come up with equations, because then they want to make predictions. If you can predict things correctly, it's better off for you, because typically, if in the world of finance or economics, you're able to make more money, right? If you're in, agriculture or, natural resources, these models and making predictions allows you to, when to conserve, and when to up production. So this type of modeling and making models is, what real world, people do in the real world all the time from all different fields. Okay, I'm sure that when we do this assignment class, we will have another example or two to go over together as a warm-up. If I have this target and the rest of the notes down here down for your notes tomorrow, we'll check it and we'll see you then. Have a good day.